Okay, so we're going to continue finding derivatives, but we're not just going to find the first derivative. There's what is known as the second derivative and the third derivative, which is just taking the derivative of the derivative and so on and so forth. So at the top here, again, I don't know why I have this here. It should really go on the back, but this is talking about our position function. We know that the derivative of the position function is velocity. So the second derivative of the position function, which would be the first derivative of the velocity, is known as the acceleration, for those of you who do physics. So position, velocity, acceleration is the progression from the original function position to the derivative of position, which gives us velocity, and then the derivative of velocity gives us acceleration. We'll jump into that in the back when we have an application, but for the first one here, we're just looking for the second derivative, which you can't find until you find the first derivative. So we first need to find the first derivative by using a quotient rule here. Bottom times derivative of the top minus the top times the derivative of the bottom, all over bottom squared. And you definitely want to clean it up before you jump into the second derivative. So that'll be 2x squared plus 3x minus 8x is minus 5x minus 12 minus x squared minus 3x over x minus 4 squared. And then it'll be x squared minus 8x minus 12 over, if I square this out, well, let me see first if we can simplify it even further. Is this factorable? X minus 12 plus 1, no. Minus 6 plus 2, no. Alright, so we may want to, the numerator is not factorable, so we'll just multiply out the denominator. And there's our first derivative. So our second derivative would come from a quotient rule involving this one. So for f double prime of x, we're just going to do the quotient rule again. So your bottom times your derivative of your top, 2x minus 8, minus your top, sorry, I ran out of room, times the derivative of your bottom, 2x minus 8. Oh boy, I did something wrong. Top times the derivative of the bottom. I did the whole thing wrong. Oh wait, no I didn't. Sorry. Bottom times the derivative of the top minus the top times derivative of the bottom, 2x minus 8, all over bottom squared. Which the bottom was this, so now I can, if I do want to keep it cleaner, I can just square that, which would make it to the 4th power. And then cleaning up the top and so on and so forth, which I'm not going to do for the sake of time, but you understand the process of now the second derivative. Here's just another one that mixes some exponentials. So we would find the first derivative using our product, first times derivative of the second, derivative of sine is cosine, plus the second times derivative of the first. So h prime of t equals, if you want to, you could factor that out, which I would recommend because you'll see in a second here, when I'm about to find the second derivative, now I can just do the product rule, first and second. If I had used this version, I would have had to do the product rule here and the product rule there, which would have been tougher. So now to jump into the second derivative, I have my first times the derivative of this, plus my second times derivative of the first, which is just e to the t, and then clean it up. So the concept of the second derivative is pretty straightforward. Here they're giving us the second derivative, asking us to find the third. So for all intents and purposes, we just need to find the derivative of this to get from the second to the third. So you'll just have to pay attention to what derivative you're on. Same thing here. So they're giving us, and this is just a new notation, once we get up to the third derivative with those primes, they'll start saving space and just using the number. So here they're giving us the fourth derivative, asking us to find the sixth. So obviously you find the fifth first, which would just be 2, and then the sixth derivative is just 0. So you just have to do the number of derivatives away from where you're starting to where you're ending. Okay? On the back we have a velocity situation of a car. They're giving us the velocity and then they're asking us for the acceleration. So this is where understanding the acceleration to be the derivative of the velocity is important. So v prime of t is going to be also known as the acceleration, is going to come from a quotient rule. So our bottom times the derivative of the top minus the top times derivative of the bottom all over bottom squared. And then we're just going to evaluate this. I'm not going to do it because I don't have a calculator here with me, and I'm just trying to get through this video for you. But you would then just find your acceleration at 5 seconds. There's no point in cleaning this all up if you can just, if at the end of the day they're just asking for a of 5, so plug a 5 in. They're then going to ask you for the acceleration at the 10-second mark, plug a 10 in, and then also at the 20-second mark. Okay, this next one gives us a boatload of information. The function value of g at 2, the derivative at 2. The function value of h at 2, the derivative on that function at 2. And then it asks us to find f prime of 2. It gives us the fact that f of x is g of x times h of x. So to find the derivative of f of x, we're just going to use the product rule. So first times derivative of the second plus the second times derivative of the first. Then we're just going to find that at 2, which means we got to take g of 2, 3, h prime of 2, 4, h of 2, negative 1, g prime of 2, negative 2. So it's just 12 plus 2 is 14. And then the last 3 examples I'm just going to jump to the book on. So on 156, number 116, it's a series of 3 graphs now, not just 2. So a function, its derivative, and its second derivative, and it's asking us to decide what is what. Now, really, based on what we know about our power rule, the highest degree polynomial is going to be your function. And then the first derivative of a quadratic is a linear. And then the second derivative, which would be the derivative of the line, would be a constant, because the slope of a line is a constant. So here we've got the original function. This would be the first derivative, and that would be the second derivative. Okay, if we jump to 132, it says if f of x is an nth degree polynomial, then f n plus 1, so that's the number derivative, would be 0. So what I'm thinking here to kind of wrap our head around it is to pretend n is like 7. So if f of x is a, well, maybe 7's too high, let's do fifth degree polynomial, then f to the 5 plus 1, they're saying then the sixth derivative would have to be 0. Well, let's see. The first derivative, if the original function is a 5th degree, then the first derivative is a 4th. The second derivative is a 3rd degree polynomial. The third derivative is going to be a 2nd degree polynomial. The fourth derivative is going to be a linear 1st degree polynomial. And then the 5th derivative is going to be a constant. So 4th degree, 3rd degree, 2nd degree quadratic, 1st degree linear, and so the 5th derivative would be a constant. Not necessarily 0 though. Whatever the, oh, I'm sorry, I did say the 6th. So then the f of 6 would have to be 0, because this constant slope would be whatever the slope of the line was. But then once this is a constant number, when you take the derivative of a constant, you get 0. So that is a true statement. And then lastly, 134, if the velocity of an object is constant, then its acceleration is 0. And again, so velocity is a constant number. Velocity at some t is, let's say, 50 miles per hour kind of thing. Then the acceleration, of course, is 0. Because if you're going at constant velocity, you're not accelerating. So that is true as well. So your homework is there at the bottom. And you may start on that with whatever time you have left after the quiz.